And we are going to cover the storage, how Substrate stores the runtime state. You already got a flavor of it by doing the assignment, but hopefully this lecture makes things more clearer. Feel like we are still waiting. Are we waiting for any of your neighbors? Yeah, I see people coming. I can wait a minute more. Okay, I'm starting now. So till now, your mental model should be like this. You should already know this. So there is some runtime stuff that you write. It's your application logic. There is some node stuff, and you use SPIO storage to access this host function to store state in your node, right? Now I'm introducing another term that we use. So externalities is a trait that provides you these host function when which you can use to save state. So think from the runtime point of view. What is host function if it is not inside a client, right? There is no host function if it's not embedded inside a client. So from a runtime point of view, anything that is not in runtime is an externality. It's just terminologies, nothing like new. So with that, what I said, I can represent the node stuff as externalities. So runtime interacts with externalities and it saves the state in the externalities. Make sense? Uh, you must have seen this yesterday as well in your assignment or today. If you're still working in the morning. Uh, we use SPIO storage to get or set a value. We pass it some key and some value. Both are opaque. There's no type information in it, so it's just a bunch of bytes. You might have already noticed also in your test, whenever you access this SPIO storage, you need to wrap it in this externalities. If you actually don't do this, you will get some error. And the reason is it doesn't make sense to save state or these host functions does not make sense outside of this node. Yeah.
So if we didn't do this, where will it be stored? You said
No, you will get some error. There is no host function, right? So test externalities in a way mimics your node in your unit test.
But on yesterday's session, we actually accessed the storage, right? Together, like when you demonstrated the code.
Yeah, so this is for unit test, test externalities, and your runtime, it already has a node folder as well if you see in your code. So it is already, the runtime is already inside the node, right? It's embedded inside a node. So it makes sense. But if you write a unit test, there is no node, right?
Mm-hmm.
And in unit test, you need to wrap things inside test externalities.
Okay, so only for tests.
Yeah.
so. The text externality is kind of like providing a shim of a node for runtime to access,
Say it again.
like a shim node, embedded node. So like, of course, in the runtime there is no node, right? Just
Yeah.
in the runtime, sandbox, right? So test externalities allows us to kind of access the node in the test.
You can think of it mimics the client or it mimics the node. So there is no actual, so externality is a trait inside Rust, and you can think externalities. There is externality even in the real chain. Your node has externality. It has its own implementation. For your test, there is a test externalities, which is another implementation, which is an in-memory database. So it's like mimicking a
Memory.
database for
Okay.
your tests.
Okay. Okay.
So from all you have seen till now, you'd think that our database is just a key value database, right? You put some key and value, right? Anybody differs?
Yeah, it's a macrolized storage.
Yeah.
Macrolized
But why? I mean,
storage.
we can have a key value, right?
We can have, but then it's hard to have those characteristics of partial revealing, partial proving of data, and other like proving of data is there while having a storage.
Yeah. I'll go to explain like why it is Merkleized. You guys already know that, but uh, bear with me. So if you think just from like if you forget all that you have learned and if you just saw these SPIO get and set, you think it's a key value database. And I mean, you said about proof something, right? And you can generate proof by, so let's say you have this database of these key values and you can concatenate every key and value and generate a hash. And that can be your state root, right? So it can work. They still have a reason why we need Merkleized storage.
Yeah, for also like efficiency on storing the data.
Yeah. Uh, Efficiency in storage and also efficiency mostly in for proofs. So we will go through that. Uh, exactly what I explained. We just do uh, concatenate all that and we can generate state root. So this could be a very naive implementation. This is not wrong technically. You can still do this. It's not efficient, but you can do this. uh, yeah, I kind of explained the reason, but I'll go through it slowly again. Uh, why we should not have what I explained, like just key value database and uh, concatenate everything to generate a hash. So uh, imagine there is a large database, a blockchain which has millions of accounts, right? There is Alice who runs a light client. What does a light client mean? She does not execute all the blocks. She just uh, following the block headers, and block headers has a state root, right? And now she wants to check her balance. So what she will do? She will go and ask a full node, what is my balance? Full node returns something. Your balance is 200. How does she trust that what the full node is saying is true? How does Alice verify that the value that full node sent her is actually what it claims it is? Do you want to tell more? Like, uh, it's not down.
I think the light client needs to request the Merkle proof for that node, for Alice balance node, then do the calculation to verify with against the root.
Can you explain, like, briefly what is Merkle proof?
It's all the like the neighbor, the sibling nodes needed
So,
to calculate the root. It's like it's a chain, a branch to the root.
yeah. So let's go back now. So imagine there was no Merkleized storage, which is what we are trying to answer why. So if you start your blockchain, you're not thinking about Merkle proof, right? You just start with like key value pair, you hash everything to generate some kind of proof, right? Imagine if we had that kind of data, what you will need
I need
to give to Alice.
every leaf to calculate.
Yeah, that's
verify.
correct. So for full node to prove that the data is correct, they need to send every single key and value to Alice, and Alice needs to calculate the whole state root again and verify against her state root, and then she knows that, okay, the full node is saying the same thing that I should get because we have the same state roots. Okay? Yeah.
So are we Merkleizing like previous states, or are we Merkleizing all of the data in the current?
So let's not go to the Merkleizing. What I'm trying to prove you that the Merkle is like a next thing, right? Before, if you didn't know about Merkle proofs, the naive way of implementing it is just key value database and you hash everything somehow, right? There's no Merkle proof yet.
Okay. Yeah, this I understand, but like,
yeah,
I'm just trying to understand, like, okay.
we will go to the Merkle proof as well, how it works. If okay.
I mean, we were taught how Merkle proofs work. I'm just trying to understand what we're applying it to, but yeah, let's get there.
Did you get your answer? Or?
I'm saying we understand how Merkle proofs work.
Okay.
But the question is, like, in this context, what is it that we're Merkleizing? But
yeah, we have still not Merkleized anything yet. Yeah, cool. We will go through that. So hopefully, I was just trying to convince that this naive implementation we cannot have, and we need a better way to generate proofs to store data efficiently. And yeah, you guys already know that. Yeah, there is another small thing, not just proofs, but if you change any value in the database, you need to recalculate the whole state root. You have to rehash the whole value to calculate the state root again. So it's not even efficient to even write data to your database. But yeah, I guess everybody knows already it's Merkleized storage. So I'll.
Okay, but wait, maybe this is what I'm not understanding. So the database is basically, let's say, accounts, balances. This person has this much, this person has that much, and then if Alice wants to verify the balance she receives from a full node is correct, then what is she comparing? Like, what to what? Like, and why does she need the whole database for that?
Right. In a non-Merkleized case, in a hash case, she needs all the keys and values so she can calculate the state root by herself.
So, okay, so to verify the state root, as in the state of everything.
Yes. So she needs to come to the same digest of the state, right? To make sure that the full node and what she has, the header, the state root, is same.
Yeah.
Otherwise, full node can lie and say something else, right?
Some value from the key value store. It's about the state.
Exactly.
Okay.
It's about trusting the node that it's not lying to her. It's following the same long chain. It's not some other fork, right? It could be like node is not lying, but it's following some other. It has become forked and it's like following something else.
Basically,
right?
She's given a state root which is supposed to represent the state, and and then we need to. I get it.
Okay.
Cool.
Okay, so if not that, what else? So what Substrate uses is a Merkle tree. You guys already said that. It's a base 16 radix Merkle tree. I will get to each term, but base 16 means every node can have 16 childs. I'll go to the other terms that we used. Merkle tree, I'm guessing you guys have implemented this, so you guys already know. Anybody want to recap this? What is a Merkle tree?
Hi, Ankan, I'm Gunjan. Merkle tree, we have. Okay, thank you. So we have a list of items, and we want the Merkle root, which is basically we just hash pair of items at the root level, and we get basically half number of items at the next level, upper level, and then again we repeat the same operation. We concatenate and hash two of them, and then next two of them like that, and then again we reduce the number of nodes at the upper layer as the half of that, then until we get one node which is basically which can be kind of commitment to the all the list members of the list.
Yeah.
Yeah,
I'll paraphrase it again. So Merkle tree is a tree structure where the values are in the leaf node and the parent contains the hashes of the child. Then there's a trie structure where we have some values at the leaf node, and to get to the value, you need to walk a path. Have you come across trie structures? So imagine there are 3 values in the database, Vx, Vy, Wz. To get to the value Vx, we always start from the root. We go to the path V, we find some node, we take a path X, we find some node, and this is the value of Vx. This will get more clear later, but hopefully, conceptually, this makes sense. Then there is a radix tree, which is just an optimization of the previous trie structure that you saw. So whenever there is an empty node in between, you can compress it together. So if you remember the last picture for WZ, this was an empty node. It has no value and it has only one path. So you can compress it together. So it's just more efficient storage and less hops. Okay. So I said that, or I asked that if Substrate uses a key value database, and it is true, it does use a key value database, but it's not storing the actual values. It's actually storing this trie structure somehow. And I will show exactly how we will even walk the path and figure out how values are stored. Yeah. Yeah. Just so when you say PIO storage, set something, you give it a storage key. And you take that storage key, you make a path on the trie, and then somehow you get to final value, which is called the database key, and then you store a value. Again, if it doesn't make sense yet, it will all make sense hopefully in a few slides. So imagine we have again few key value pairs. Let's say we need to get a value AE. So this is, if I have to read that value, the way I will do, again, I start at the state root, the red node, the hash of that node, whatever you hash it, that's the key in the actual database. You get the node. You read that node. From that node, you get some paths. You find the next node. Similarly, you find the next node, and you get to the value AE. We'll have more concrete example as well, but is it making little bit sense yet? We will walk the path again. So this is just to give you a picture of the actual storage key, that AE that you set in SPIO storage is not how it is stored in the database. That's all I'm trying to say till now. Yeah.
I think I missed something because it's not clear for me how you store a hash of both key and value. You sum them and hash, and then you at the like this specific node of the tree, you have a hash of both key and value. Because you're talking about the structure of the tree, how the values are stored. But where is the key and where is the value? Are both concatenated, and then we have a hash?
So I might have confused you. So the concatenate example that I was giving was an alternate example if we didn't use a trie or this radix tree structure.
Okay.
This is now Merkleized, and let's give it 5 more minutes, okay? I'll go through a few more slides where we actually walk the trie and like try to insert something or get something. If it's still not clear, I will get back to you.
Okay.
Okay. Yeah, I just also wanted to show that this the starting point is a state root, and we always keep track of it, and that's how we start walking our trie. But let's do what let's try to understand how it's stored in the database. So just to, to start off, let's make few assumptions. These are correct assumptions. Some are correct, some are not exactly how Substrate does it. For every block, we keep track of the state root, right? And for our example, we will take the case of base 27 just so we can use English alphabets and underscore. So there are 26 alphabets plus 1, 27. And we will try to read the balance of ls from our trie structure, from our database. First thing we will do, we know the state root, right? We have it saved somewhere in a well-known, like hard-coded, let's say, storage key. We know the state root. State root is a hash. We read the hash from the database. We get some value. All good till now? This value is an encoded node, right? You decode it, and you get some value. Once you read that value, you get like some children's, right? And I want balance ls. So balance ls should be path B, because every letter, the path always is every letter, but then it's compressed. So path B, we see in this node that there is a path B and it has some hash. I take this hash, I query it, I get next node, green. So now I will decode this node. I got to this node, I will decode this node.
Why A is included? S and
I mean, it might be there and it got deleted. Doesn't matter in this case, but yeah, and it's also pseudocode. So yeah. But in this case, A equal to none means it doesn't exist. So I got this node, I decode it. Again, it has some children. I want ls, so I will go with the letter A. I get some hash value, query it, get a encoded node value, which is this, and I will try to decode this now. Now we are, when you get to this, you just went to the path A, right? But there is a path that like shows the actual whole value because it's compressed now. So you need to know that you came at ls, not A something or just A, right? So path says that you have come to the right value and you have this value now. That is your actual, when you said balance is ls, save the balance as 10. That is some 0x 1, 2, 3, 4. That's our balance.
Yeah. So in the leaf node or branch node, let's say, like in the end node of the key path, you will find the compressed whole path like written like embedded in the node. Like say this is path Alice now in full, and the children's none and the values here, right? Or are we querying the value also in the DB? Because
I'm not sure if I exactly got your answer, but I'll try to say something and hopefully you understand. So imagine there is another key, Ellison, right? In that case, ALISON. So when you query this, you will get the path ALI, and it will have two kids, S and C. And again, you will go to the S or C, whichever you want LS, so you will go to the C. At some point, you will get to the last node. It might be like just the last letter, or it will be the whole path, but you will finally get to the end node at some point where it will be like balances underscore LS. It might also have, so this also can have child more,
Yeah.
but you want LS, so you will stop here.
Okay.
Does
Yes.
that
But,
answer?
yes, but then concerning the value, aren't we getting the value in the? Okay, okay, that is
So,
the queried node from the database, so it contains the value. Sure.
so, so every intermediate node can also have a value.
Yeah, but when I'm saying querying it into the from the DB.
Can you repeat the whole thing?
Yes. So the node contains the embedded value, or
Yeah.
are we kind of okay? Does it contain the full value or the reference to the DB?
Okay. It's a good question. So the answer is both. So it depends, and I'll go through it later. If it's a small data, it stores embedded. If it's a big data, then it stores the pointer to it. But for now, you can assume that it's embedded. I will show you the case where it's a pointer.
Question?
Where?
May I?
Yeah. Yeah.
So I'm not sure I understand like the where we get the characters for the children from.
Okay.
So if we look in this one, like Alice, the children for that. So or maybe let's go back to the one before the first one. So it's like the first one is we go to the left node. The first letter of that one is S, right? Like in the yeah, in here.
Is it the correct node?
Yeah.
Yeah. Okay.
So the children of the root is like B and C, right?
B and
then
S.
we go left node, first letter.
No, we go to the thing that we want to get. So we want balances underscore LS, right?
But this is the red one. Like I see red.
Yeah, you see
and
the
that's
red.
referring to A.
That's referencing to the root.
The root marked as A, capital A.
Yeah.
Right?
Yeah.
And then we're saying, okay, this is the root, right? Path, it has no path because it's the root. And then the children of it are as follows. Left node.
No, so the children is S, B, or any other.
YSB.
So that's how the Merkle tree, that's how this structure works. So you have path on the trie structure, and you traverse a path to get your value.
Why are they called S and B and A? Where are they coming from?
Right. So it's base 27.
Okay.
Right. That's what I made an assumption. So it can have all the letters in our English alphabet as kid.
Okay.
And it's always one letter.
Okay.
But then if it can compress things, it can compress.
Like I don't understand.
Okay.
Like how do we get the character S and the
So-
character B
so-
from like what's the algorithm?
Okay.
here?
So imagine a binary tree,
Yeah.
right? In binary tree, you will have two
Yeah.
child, right?
Yeah.
That's 0 and 1.
Yeah.
That's base 2.
Okay.
In base 27, you can have 27 children.
Uh-huh.
Letter A, letter B, C,
Yeah.
D, till
Yeah.
Z.
Etc. Yeah.
Yeah.
Okay.
So every node here can have up to 27 child,
Okay.
right? And we want balances LS, which starts from B.
Okay.
So I'm looking for the child B.
Like the system, we don't care about the system.
We
because
don't
I
care
just see
about
the color
system.
blue here, and I see hash B.
No, you don't. I mean, that's our full database. I mean, not full, but that's showing the database. So rightmost column you're talking about, right?
I'm talking the blue is on the left. The system.
Yeah, we don't care about this. We don't.
Okay.
There is this child S. We don't care about it.
Then why is it in the children? Like in the children, S equals sum hash B. blue.
So if we wanted to query system underscore, we will also go through the same thing, right?
Okay, so we're putting them in the children because.
Yeah, so the root will contain all the paths. We don't need to go to all the paths.
Okay,
We go
so
to.
Cool. So
Yeah.
so that's what I was saying. Like S is the first letter of system.
Yes.
So the value of S is hash B.
Value fs. Yes, that's
Yeah.
correct.
Okay. And then B is balances. First letter of balances.
No, no. Okay, maybe that adds the confusion. But what you see the node B, that's just to like that's for us to tell you like, okay, this is a node, but don't think of it as children. Okay, sorry for the confusion, but this B does not mean B for balances. It's just indicating
No,
node
I
B.
get that. I get that.
Okay.
That's a capital B, and
Yeah.
that's a capital C. But the value of node blue node capital B is
S.
Yeah, it's put in the as the value of the key lowercase s, right?
Yes.
The first child.
Yes.
Cool. Now second child, lowercase b.
Yes.
The first letter of balances, hash of capital C, right?
Yes.
Yeah. Okay.
Yes.
Cool. And then in the next one, so here, so the children of the green one is okay. Now I get it.
You got it?
Yeah.
I can pause for a bit so everybody.
No, I don't
just
get.
digest.
I don't get where the B. So in the next one, the pink one here, the B. So the second member of children. Where is the B? No, next slide. Yes, here.
So here the child don't matter because we already got to balances underscore
so
ls.
Like A and B, like it's just like following the one.
Yeah, it might have more childs. The ls, there could be balance ls something, right?
Okay, so are we basically saying that in every children array, all of the characters would exist? They would just map to none, if they don't have anything.
Yeah, it could exist. Yes.
So all of them.
I mean, the intermediate nodes where there is no value in this optimization that we do in radix tree, it's all compressed.
Okay.
But any intermediate node can have a value, and then it exists in your trie structure.
Like Alice has A and B, although she doesn't have any children.
I mean, this is none, so it means it has no children.
Okay,
but it could have a children.
Equivalently, in the previous one, then this theoretically also has like C and D and Z mapping to none.
Yeah.
Okay.
So imagine you have a node, and each node has an array of 28 of nodes.
Yeah. That's
clear. I'm gonna pause here. Just any more questions? There is actually on my next slide there is this link. It actually is a visualizer. What happens when you insert something or try to read something, and what happens? So you can actually scan this, play with this for 5 minutes, and 5 minutes I can take more questions also if anybody has other questions. It's good. Okay, should we move on? Let's move on. Okay, back to our question that we asked in the beginning when we had non-Merkleized storage. Do I have the attention? Now with our Merkleized storage, imagine again Alice is the light client, it has only the state root. How can she query her balance and verify that her balance is right? And I'll just tell you like, this is, imagine all the key value pairs that we have in the database. And the blue ones are the ones that will be given as proof. And I'll just let you for 2 minutes see this, and hopefully it makes sense a little bit by yourself. If not, I will explain. Yeah, so Alice will get these blue nodes, the solid blue ones. The dotted blue ones are the ones whose hashes are already contained in the nodes that are provided. And the yellow ones, we don't need it at all. Is it understood or questions? Okay.
Yeah, like, so right now, Alice is being given a proof, and like, here's a root and here's a bunch of nodes, right?
No, not exactly.
Then what
So,
exactly?
so I'll explain. So Alice wants to make sure the value in this is what she's querying, right? The full node should return the value of this thing. And she wants to verify it's correct. It belongs to the same state root that she has. So she will be given all these solid blue nodes, right? From the first node, the state root, you will get the hashes of this. You don't need the actual node, you just need the hashes, right? You get this full node. From this, you get the hashes of this, and this, you need the whole node again because you need the value of it. And from just this 3 nodes, she can calculate the whole state root and come to the same value that she has.
Yeah, like that's the Merkle proof that we did.
Yes.
Yeah, okay.
Yeah.
I'm just trying to understand what because when we were taught the Merkle proofs, it works by like the prover gives a root and a list of nodes, if I remember correctly, a list of like nodes.
Yeah. So those
so
3
what I'm
nodes.
trying to understand, which one is the prover giving here? Is it
Yeah.
the
solid blue ones?
The solid blue ones. Okay. Okay.
Does it make sense? Can you just raise your hands if it makes sense? Don't wanna just go along and okay, at least few hands. I can't hear you. Is it off probably?
So given 3 nodes, Alice will be able to, so we also assume that Alice is able to query the database because given the root hash, she will need to query the database
No,
and get
she
the
doesn't
detail.
have the database. She's provided these 3 nodes. And from that 3 nodes, she can calculate the state root, she can get her balance, she can do everything that she needs.
Okay, so by providing the node, you mean the key as the hash and its value decoded?
I mean, everything is sent over the wire encoded. But
Okay.
the value of the nodes, the whole node is sent to the.
Okay, so key
to the,
value both is available.
Yes.
Sent. Okay, okay, makes sense. Thank you.
I mean, key value. She already has the state root, which is the key, but she just provided the value, right?
Oh yeah, value. Got it. Thank you.
So, but in theory, here, so in theory, we don't need Kian, Alice, and Bob because we already have balances, right? And
Say it again.
so
Balance. Yeah. Okay, let me
because
think.
it's the hash of all of them already, right? And we have present the system.
Yeah, but you don't know which kid. Okay, you do know that.
Because we have the three top already, like balances, system, and parachains, and we can get the root, right? Or
you're talking about the Alice node, right? Yeah, but I mean, it can have more cases. I'm just imagining cases where you want to know that the value exists in this case, in this place.
okay.
Yeah. Yeah. I'm not extremely sure, but I think you might need this as well. So you can have, let's think.
So we are trying to prove that Alice has this balance, right? In the whole thing.
Yeah.
Okay.
I mean,
In
I don't know.
this case, we will need to check the hash of Alice, Bob, and Kian together and make sure that they are equal to balances, right? That hashing them together will be balances.
Yes.
And then check balances, systems, and parachains,
Yeah.
and that they are equals to the root.
Yeah. So actually, when I said she wants to get the balance of Alice, giving her the value before is kind of same as saying you give her 3 nodes, right? The value is contained here. So you give it this and you actually can calculate the whole hash of this as well.
Yeah.
So you need this node as well completely.
Ankan, I have a small confusion over here. So when Alice wants to when Alice wants to verify that it's coming from the right source, so when we are sending these 3 nodes, so you mean the top node and then the balances and then the Alice, or is this the bottom 3, Kian, Alice, and Bob?
No. The solid blue.
Solid blue.
The state root, the balances underscore, and the
Okay,
Alice.
so these 3, so the hash of all these 3 nodes she will has, right? The hash root.
I mean, if she has the node, she can calculate the hash herself.
Okay, she has a state root, right?
She has the state root.
Right. So now she will get the hash of all these 3 because all these 3 nodes has the hash, right?
Yeah, but I mean, if you have the node, you can calculate the hash of. The hash of it is just the hash of the node, right?
And the balances node has the hash of all these 3, Kian, Alice, and Bob.
Exactly. So if you remember the children of any node, so any node has children's, right? And it contains the hash of these, of its child, right? So it has the hash of all 3, but you need the whole node this so you can hash this and make sure the hash is the same as hash of the A children of this, right? And for this, you don't need to care about the values. So you just get the hashes from here. You hash them all together to get the hash of this and make sure that hash is correct. You do the same thing with the state root and you come to the final hash.
Yeah, so the balances node, I mean, as per the Merkle rule, right? So generally it stores the single hash of the child nodes, leaf nodes, right? So Kian, Alice, Bob, so calculating all 3, we get one hash and which is stored in the balances node, right? Now after that, another round, if it's the same level, we have another child, it calculates the hash of all those nodes and stores the root node, right? That's the final hash, that's root node. Now, when we are verifying with the Alice balance, so when we navigate, to the tree, so the balances node has a single hash, which is the hash of all these 3.
Okay.
Now, when we are so the state root which she has, which is same as the one which is the top, right? Now, when she verifies, then I mean, the balances, and I mean, these three nodes, I mean, when we provide these three nodes hash, won't be, the hashes won't be different, like, because this balances has the hash of these three nodes together in one node, right? I mean, my confusion is like, because we are verifying just the Alice.
So what we need to verify is also that the hash contained in the balances for Alice is actually of this node, like this whole node. So we want this whole node value to get her balance, to hash it, to see that hash is correct. But the other hashes, we don't care. We just care that there is a hash value. And if hashed with all three together, if all three are hashed together, then we can come to the balances, right? We don't care about the actual values of this, what is inside this. Does that make sense? So you just need this node, not these. The hashes are there in the value of this node.
So hashes, when you say we have hashes, you mean the hashes of each node? I mean, three hashes in the balances node?
I can go back to the. So what does the node value contains? Maybe. A node value contains the hashes of the child. So you only care about the hash that you want to query, and you want the whole value so you can hash it again and check if it's correct. But the other ones, you just take the hash. You don't care about the actual value. So the Kian and Bob child that it had, it's already contained in the balances underscore node. And you don't care about those hashes are correct or not correct. You just have some hashes, that's all. You only care about the LS child, that's all.
Okay.
Hello.
Okay.
Can I go back? Okay. So to understand this, now you have two nodes. The first node is you just got the hashes, and the other node has to complete the hash and the value. And then you ask that node for a value of Alice, like a balance, and he will give you the balance amount and the three nodes.
Okay, no. If you want to query LS balance, it will just give you these three nodes and it will figure out the balance itself by reading the node.
So just the three nodes.
Yeah.
Thank you so much.
One question. So, I don't know. Is possible to one node it's at the same time a leaf? Because maybe imagine this: you have Alice, and you have also Alice Cooper.
Alice.
So, Alice Cooper, secondary account. So Alice Cooper is going to be a leaf from Alice, and then Alice has its own value, but it doesn't matter if Alice Cooper modify its value, right? Its balance, because
it doesn't.
The value doesn't depend on Alice Cooper, but the hash of Alice is modified if the children's are modified.
Yeah.
So maybe it's necessary to compute the children's or not.
No. So you have in a way you have the hash of the child's, right? Right? And you don't care about those values. You care about the value inside this. So you have the child hashes, you have the value, you take the hash of the thing and you verify. And
Okay, so I trust in the hashes that I have in the vector of hashes. So I compute this, and it's supposed that this must be exactly a hash of the Alice node, right?
I didn't exactly get it, but so you do you like trust understand that? So you only care about the value here, and the child nodes you just care about the hash, and you already have that hash. If Alice has more children, you don't care about those values. You care only about the hash to calculate the hash of this node and the parent nodes, right?
Yeah, but the node is affected, the hash of the node is affected if the children's are modified.
Yeah, but you don't care about the children. You just care, you have some hash, right? And if that hash and the value
Okay.
comes up to some
Yes,
hash,
the hash
then
of the value. Yeah.
okay, there's one more question, and then I will move on.
Okay, so what will happen in the event? Let's say a key is deleted from.
Alice is deleted.
Yeah, a key is deleted. What will happen to the entire structure, if I can say so?
This one is deleted. Alice.
They're being stored in key value pairs, right? I mean, starting from the state root, going down to the branches, all these nodes, what's stored inside them are in key value pairs, right? So is there a situation where, let's say, inside one of the, whether it's a leaf node or the state root, one of the key is deleted? Yes.
How do you prove
Yeah,
it?
what happens next?
Yeah, I mean, in the visualizer, you can see how it's deleted. But is your question how the deletion proof? Like, how do you prove that something is deleted?
No, not proving. I'm just curious. We're
What?
storing inside of these nodes. We're storing an array of key value pairs,
okay.
right? So inside of it, in the event one key is
Is deleted.
Yes.
Then
what happens?
So imagine a child of Alice is deleted. The whole hash is changed
the
now.
key inside.
Yes. So
yeah.
one child, the key inside. So one child is in a way deleted, right? It's kind of same thing,
Yeah.
right? The whole hash is now changed because the hash of the node depends on the child and its value. So this is changed. This hash will change. Everything on the path will change. We have to recompute it again. The state root will change.
Okay, so multiple deletions can happen concurrently at the same time.
It could happen, and then we might have to recompute hash with as many nodes that we need, in theory. Okay, we took a lot of time here, so hopefully it makes more sense, but I'll move on. Yeah, important thing to state that having efficient proof size is a big win for light clients, and we use light clients a lot in Polkadot, so it's a great thing. To recap, the storage key when we see balances underscore ls is actually a path on the trie. It's not actually the database key. This we actually didn't see it, but storage key we did see it. So storage key can be arbitrary length. In some blockchains, I think in Ethereum as well, the keys are hashed by itself, and you always have the same length of the key. In Substrate, you can hash the key. You don't have to hash the key. You can concatenate, so you can have different length of keys. You will see the examples how it is used in Frame. Intermediate nodes in a trie can have values as well. You already might have seen this. Colon code contains the actual Wasm blob, but there could be something else also as a child, and it can also have value. We already saw that. And when you do something like SPIO storage get balances underscore ls, it's not one database read. It could be multiple database reads. So that's also something that you need to remember. It's never, or it's not, unless you're doing a state root read, it's never one database read. Depends on how many times you have to hop.
So what happens with like when we add the new nodes in the trie, like basically the edits? So currently we have a hash, like the keys are the hashes and then to the values. But then if these values changed, the hash will change, and then I will need to change it everywhere else, right?
Yeah, you have to recompute the whole thing.
Okay, so when we add something new, we are a pre-compute the.
Yeah, I mean, it kind of works like a proof only if you think about it. Only the nodes that are impacted in the same line would actually be modified. The other parts that are not affected, you can just take the old hash and
So
recompute
it's
with the
still
new.
log in.
Yeah, it's okay, I mean, but you have to recompute.
Thanks.
But it's less computation than if imagine you did the whole concatenate of the keys. Okay, so now after all this, your updated mental model should be runtime stuff, some way to access this externality. There is a database, key value database, but on top of that there is a backend, which is a try backend. This layer is called like a backend. It can have different multi implementation. We saw a try backend here. Okay, this question was actually asked, and oh, yeah, yeah. So yeah, so the question was that can I differentiate between storage and database key? If you remember the balances underscore ls that we put on SPIO storage on the runtime side, that was the storage key. Your runtime thinks of it as like only I know the storage key, get me the value, right? But internally, you need to hop few things. The actual database stores like ls encode, like the node of ls, right, as a hash. That is the actual database key in your database. So this is your database key, right? The actual balances underscore ls was your storage key. The actual database keys are these. So you have to hop around and get it. So one storage key can have multiple hops, multiple database uh, queries to get to the actual value. Make sense?
Yeah.
Database keys are actual keys in our underlying database.
So you just concatenate the storage keys, and
It's
then,
not. It's you need to walk the try and figure out the value, right? It's not concatenate.
So, for example, you are looking for Alice balance. So you know the path, and then you just look at the storage key. You use the storage key to find the node's information, and then follow the path, and finally get the database key and
So
fetch the data from database by using the key.
Yeah, you're right, but everything is a database key. So when I say database key, what I mean is balances ls is not a key on the database. We call it a storage key, and the actual keys that are stored on database are multiple try nodes, right? That's what I mean. So there's no balances underscore ls directly in this, right? You need to walk a path, and it's something else completely different on the actual database. We can talk about it again after it because I should have been finished by okay, we can go a little bit more. This question was asked. So you saw the proof, right? Proof is like from the state root till the actual node that we want to provide the proof for. That is the thing that you have to pass as a proof, right? Imagine you have to provide this value. So to give a proof, you have to give all this nodes that are on the path, right? But imagine one of the nodes has extremely large value, right? Then what happens? When you give the proof for this, you actually transfer over the wire the value of this, which could be really big. And that was the question I think one guy asked. And the way we circumvent it is, what happened? Yeah. So the problem is that the data that you're transferring to another node is really huge, right? This node is like really big, and you have to pass the whole thing to the other light client or anything to show that to like show them the proof that this is correct, right? And you don't want to transfer too many things over the wire. So in this case, basically what we do is can actually stare at that picture. Instead of keeping the value here, we put a pointer and we actually put the value in another place. So the actual value is now put in another node, and here you put the pointer. So there you put a pointer instead of actual value. So what does it mean? It means the proof size again becomes smaller. But the trade-off is that now you have multiple hops if you're reading something from database. Right? One extra hop. One extra hop. Yeah. Mike?
Sorry, is the pointer also a hash of the big stuff? Then
Yes.
the big stuff stored in the key value storage.
Yes.
Okay.
So it's the hash of the value, and you put the hash in there, and there are like enum variants. This is like very naive example, but like internally you can have a variant and say, is it actual value or is it like a pointer? And then the actual value is at the
hash
another
as the key to the
yeah.
Okay.
Okay, we talked about like how you have to traverse the trie. There could be a situation where one side of the tree could be unbalanced. So imagine you have a structure like this, and if you have to query balances underscore ls, it's like 2 hops. And for getting balance of Kian, you will have 6 hops, right? Do you think it's a good thing? And when we make like when we build our blockchain, our runtimes, I mean this is already mentioned. We don't have gas metering in substrate chains. What you do is some kind of benchmarking. So you might have come to the benchmark that reading any balance takes 1 second. So let's charge fees of 1 second computation, right? But for balances balances Kian is taking way longer than balance ls, right? So it could be like an attack vector where some parts of your code actually takes way more time than the fees that you are charging. So it's important to make sure your trees are not balanced, not unbalanced. How do you do that? How can you do that? Anyone? Mike? This.
Can you like basically level downwards, like make Alice A-L-E?
No, we don't want to change our structure.
Okay.
Yeah, what we can do is anytime when there is a code path that somehow user can influence what would be the key. We don't want to have that, because then if user is able to influence where the keys are stored, they can attack your chain. They can like make it unbalanced by calling some extrinsics that are like gonna put only keys on one side. And if there is a code path that does that, what you want to do is use some kind of cryptographic hash so it's distributed. So it's not predictable where the keys will be stored. You will see how Frame handles it. But yeah, that's the gist of it. Does anybody need a break or should I keep going?
Let's go.
Okay. Okay, if you now have seen, if you have already done part of the assignment, right? And you'd have seen that uh, the the Merkle root is only calculated at the end of the block. So when we do finalize block, right? At the initialize block, we get some root, we change, we apply extrinsics, and we calculate the root again at the end of it, right? So imagine all the extrinsics that you're doing within a block. Imagine you have to do so many database reads, database hops. So imagine in one block, you modified balances ls 5 times, and you have to do hops of ls. Let's say it takes 4 hops for reading balance of ls, and you did 5 multiplied by 4. So 20 database reads you are doing, right? Which is not very efficient. And what we can do is cache. Yeah. So what we can do is have a block scope cache for storage, and this is already existing, and I will show you how it works. Yeah, it's called overlay. It's a cache layer of the runtime. It's just key values. There's no trie structure now. It's over the trie structure. It just key values and only for block scope. It works similarly to most of the like CPU caches that you have seen. If you read something that does not exist, it caches it. Next time you read it, it stays there, so you don't have to go to the database. You just read it from the memory. So it's cheaper. You write a value, it's written there, and it can be read from there only as long as it stays in the cache. And all the changes are flushed only at the end of when the block is finalized. Yeah, we don't have any race condition because runtime is single threaded, so useful. I'll show you an example how this works. Imagine we have to, so we are starting a new block. The first extrinsic, you're trying to read some key called ls, and it does not exist in the overlay. So you go to the database, go through your trie, go to the database, you read the value, you cache it, and you return the value. Second time you read ls key again, you don't go to your database, you don't go to your trie, you just read it from the cache and you return it. It can't change. It's single threaded. Who can change? So it's only one thread that is doing, and it first one didn't change it, second one didn't change it. Yeah, we will see actually, but there has been no write till now, right? Even the write will go through overlay. So any changes will happen in the overlay before database. So third extrinsic, it sets Bob value to some something, 42, I think. It's not stored in the database yet. It's only stored in the cache. And then imagine we store in the same block. The block has not finalized yet, same block. We update the value, or we somebody sets the value of Bob again to something else. Again, just update it in the cache, not on the database. And when you actually finalize, this goes through trie, and actually writes the value in the database. Did that answer your question? Is there a mic?
So in the right time, while writing, we are updating the overlay, and as the extrinsic writing is progressing, we are writing it, but at the end somehow we get the error, so we do not write anything in the main database. So do we unwind over here also?
So it should be infallible. It should never error. If it errors, it means the block didn't finalize.
Yeah. So while finalizing, if error comes,
okay, then whole block is gone.
and
There's no block.
the updates in the overlay.
So every time a new block starts, a new cache starts.
Oh, new cache.
You never reuse the same things.
Okay. Got it.
That's gonna be hazardous.
Regarding the gas, well, the metering of the instructions that we talked about, do we charge like different values if a previous transaction read the value, for example, and we have it ready, or is it the same?
No. You will learn about it in a benchmarking module. I think it will be in the frame section. But the TLDR is that you set up some conditions, some worst case conditions. You benchmark your extrinsic with random values and random like parameters, and you calculate like some kind of average or different cases, and you can in your code as well, based on which path it took, you can charge different values. But it will never be on this. So from your runtime's point of view, it's only kind of one storage read or write. So you need to try to make sure you don't have unbalanced tree. As long as you don't have unbalanced, the benchmarking would be correct. It would be like balance LS might be way more expensive than system underscore block number, right? So if you benchmark correctly and if you don't have unbalanced tree, it should be fine.
Okay. So basically, if there's a block that's full of transactions modifying Alice, we are going in a way to overcharge the transactions because for us they're going to be easier.
Yeah.
Okay.
Where does this overlay live? And the other question is the try just a visualization of how the database like structured? Actually, there is no like physical try there.
Yeah, so try is more like a data structure, right? So your database is kind of represents a try, and it's just some algorithm to figure out these values. It's not really a physical data storage. I mean, the physical thing is this database. And the first question was, what was your first question?
First question is, where does the overlay
live?
Layer, where does it exist?
So it's on the node side. Everything is on the node side. This is runtime. Everything on the right is node. Okay, I said it's cheap, but you have to remember that it's still not free. As in, you're not hopping database, but you're still crossing the boundaries of WASM. It's on the node side, this overlay, which means you still have to do serializing, deserializing. So it's not free. It's cheap, cheaper than database reads, but it's not free. Okay. You also have the option to have child overlay. So imagine a use case where you have some piece of code, and in between the code, you have some transactional piece of data. So something should happen like atomically. And if something fails in between, you reverse the whole changes. So there is a concept of child overlays, and you can use this something called with storage layer. And whatever you write within it, if at the end of it you return OK, those changes are committed. If you return error, then those are reverted. An example is you write with storage layer, you do something, and what happens is it creates another child overlay which copies the first overlay and then makes changes there. And then it will be merged to this if return success. Yeah.
Wait, can you repeat? Why do we need child overlays? Isn't it like a computation? Like we are doing like same computation again and again. Like why should we copy and then change then merge it? Why can't we just change in the overlay as it is?
So if I understand correctly, why we copy the whole thing?
Yes, like why are we copying and then changing then merging again?
So I think it does some optimization. So if value is not changed, it just points to that value.
Okay, why can't we change in place? Why should we copy, change the copy, merge to the
Because
main?
that's the point of it, right? You want to have this transactional piece of code, and if it errors, you want to revert these changes, but not this.
Also, you're okay. So overlay contains different, let's say, sections of store.
No, so this is only, so maybe you missed the last one. So this is the case only if you want to have a small piece of transactional code in your main piece of logic. So the extrinsic is already transactional, but inside that you want to have some small transactional piece of code that should change everything if everything passes, else it should revert all the changes. So it's up to you, it's your business logic. If you want to have a nested transactional piece of code.
Okay, let me repeat.
Okay.
The overlay change set, right?
Yes.
Yes. It caches the, if you query something, it just caches there,
Yes.
and if you want to query again, you just take the value and not go through the tries and everything, right?
Yes.
So it stores the cache there, and if some values change in the try, it will change. Of course, okay, it will be deleted in the overlay until you fetch it again, then to be cached in the overlay, right?
Repeat the last part again.
If we have, for example, I queried one, okay, the key is, let's say, is 1 and the value is 20, right? If I query the first, it will cache the 20, right?
Yes.
But then if I change my value, let's say 30, right, it means to be deleted in the overlay because it won't reflect the value, right? So the overlay won't have the value of key 1, won't have the value because I've changed my key, until I fetch again.
Until you find, I missed, I didn't
Okay,
understand,
okay.
sorry.
Okay. In the initial state, there is no any cache, right?
Yes.
Only try in database, right? I have the key named 1,
Yes.
key, right?
Yeah.
Okay, so let's say key named ratio, right? And the value is 20,
Yep.
right? If I query, the 20 will be cached in the overlay.
Yes,
So
correct.
next time I query the ratio key, I'll just get my 20 on the overlay change state.
Yes.
Right? So if I change now my value to 30, it means it will be deleted in the overlay because it won't
Yes.
reflect the value, right?
Yes.
So if I fetch again, it will be cached that 30 value.
20. The new value.
30,
30,
yeah,
30, yeah.
30,
Yeah,
you know?
the new value.
Okay, so now overlay change set will have the 30 value, right? So my question is concerning the storage now, the child overlays, right? You said if you want to have a business logic which kind of reverse and change, that's why I didn't get it, like how does it relate to it?
So first thing is,
I think there is something missing. He's saying that when we write, you delete from the overlay, but that's not what you said. When you write to the overlay until the block is finished, and then you delete.
Yeah, I don't delete anything. So everything is single threaded, so you don't have to worry about it. So if you write something, it's written in the overlay.
Yeah, you can get the slide
Yeah.
for the overlay. Yes, this one.
So when you write something, it's written in the overlay. It's not flushed to the database until we finalize the block. And if you, so first time you write 42, next time you overwrite it, it's again only updated in the overlay. Yes.
Now the story child overlays now. How do they come into place there?
So imagine you did the set and now you have some big chunk of logic in your next extrinsic, and inside that you want to write another small piece of transactional code that should either commit all the changes. Imagine this does few things. So it's setting bar value, right? And maybe few more things, setting Bob value, setting Alice value, right? And it does something, and if something goes wrong, it should revert everything that it did in this block, nothing else. Okay. So it's just a small transactional piece of code that you're writing.
Okay, so the transaction piece of code affects many storage entries, right? If it's successful, it will change, manipulate like a lot of.
If it succeeds, it will change your overlay, the main overlay. If it fails, it will revert this, it will kill this. We go back to the initial state. Okay. And then the same thing repeats. If it finalizes, it is reflected in the database.
Okay, so for example, if we remove the child overlays, we can literally work with only the main overlay with those changes.
But how could you? So imagine you are manipulating Bob and then something went wrong and you want to revert the changes in your transactional piece. You lose that change now, right? Here.
It's like snapshotting. You snapshot this and then like change, and if you can revert easily.
We can take this offline as well if I'll try to go fast a bit now. Okay. In favor of time, I'll just answer this. So the question was, can your overlay calculate a state root? And it cannot, because it's a key value database. It's not a Merkleized storage. And to calculate a root, you need to flush all the changes to database and then calculate the root. But generally, you never need to calculate root. You only care about it at the end of a block. There are all different kinds of caches as well. This is just one cache and overlay, but you can read about other caches substrate nodes use by just like searching for cache in the substrate, say like subcommands. Okay, now the updated picture is runtime, SPIO storage, and your externalities contain these pieces. You have a underlying database that is backed by a backend called try, and that also has a cache layer which is overlay. And finally, I think I talked about this a little bit before, but so for your test, what you use is test externalities, which has an overlay and a try DB, which is an in-memory backend. But for the real thing, it's also called ext. These are also linked, so you can actually find the documentation from the slides. But this also has an overlay and a try DB with a real database, which is like Parity DB or RocksDB.
Question, hello. For the purpose of the assignment, like we're not supposed to be implementing this, but we're supposed to be aware.
I mean, ext is already there in your actual node, and the test externalities, you are using it.
Yeah,
you don't have to implement.
Like it's there.
Yeah, it's there.
But like we should be aware of it, I guess.
Yeah.
Because like what we talked about, performance and cache.
Yeah.
Yeah. Okay.
And for your assignment, you don't even need to care about that. But you should know about this as a runtime developer. Overlays in memory of the client. So, yeah, I don't want to say something wrong. Oh, what happened? What? Yeah, but I think for test externalities, everything is, there is no, for unit test, specifically, there's no VASM or anything. You're just writing your unit test, right? So that's in memory as in just one, right, like one thing, right? But in the actual thing, it's still on the client side. So even if it is in memory in the client, you're still going via this VASM bridge, right? So it's not cheap. Yeah, and I talked briefly about this. So if you don't wrap this in test externalities, you get this weird error. It's kind of, I don't know, it says something like called outside of externalities. It's not super useful to read and understand, but if you get this error, you should know that it's because you missed wrapping it in test externalities. Basically, you cannot access any host function outside externalities environment. Okay, I don't know how many. I hope it might be the last. Yeah, I'll just cover this, and this is very short. Okay, last two topics. So till now we have mentioned few times that there is a state associated with every block. And you might think, then database is storing so many things, right? Like for every block, it's copying the same state again and again. Does that make sense? No? What do you think? How is it storing the state? So the way it works, so everything is like linked to each other, right? So it's like a pointers to different data. And for block n, let's say there is a state root, these keys, the actual values at the bottom. And at block n plus 1, I think if I'm not wrong, imagine only this value is changed, this node 7, right? So what will be the new state? So this node is changed, which makes sense. This node needs to change because now its hash will change because its value has changed. So this needs to be recomputed. But the other side of it can just point to the other child, which has not changed. Similarly, only the nodes whose hash needs to be recomputed gets changed, and everything else is pointed to the old value, right? N plus 2, this node is changed, and exact same thing happens, right? I'll give a second. So imagine if we want to prune the storage which are like more than 1 block old, or yeah, more than 1 block old. We need to now remove the storage that belongs to only block n and nothing to the block n plus 1 or n plus 2. We just remove all the storage that does not belong to these two states. And imagine now if there is a state that never changes, it kind of stays same forever. You never read or write or do anything with it. It just stays there. So it's not extra computation every time a new block is created. Just to note that by default, if you run a substrate node, I think it's 256 blocks that we keep state for, but you can change this if you want. Yeah, I already talked about this. Child trees. So there's another nice feature of substrate that generally is not used a lot, but this is a base 16, a very opinionated format that substrate uses. But imagine you want your own trie structure. I don't know, you want to create like keep track of the state root and have some proofs of what data your child tree contains. what you can do is use this child trie. For the main trie structure, it's like just one child, but internally it's another Merkle tree storage structure. It's not used so frequently, but it's actually used in, if you know about Polkadot, there's a crowd loan thing. So in crowd loan actually uses this, so any contributor can actually prove that they have contributed to a particular crowd loan by proving through the Merkle root of this child trie. For smart contracts also we use in some places.
We do this for extra optimization for the storage as well, or what?
So we use this if you want to keep track of your own state root for like your child thing. So imagine you don't want to, you keep track of this, but let's say crowd loan, right? You want to, so the way we use it is every crowd loan maintains this trie structure that has contributions to it. You know about crowd loan, right?
No.
Oh, okay, sorry.
Trying to.
Okay. Crowd loan is a way to, like, it's like a crowd fund thing. So you put funds at one place and buy like one slot from Polkadot. I don't know. Does that make sense? Do you know about it? Because it will all be covered in way later section. So if you don't know,
No,
I should not give that
familiar,
example.
but
okay.
So I understand this concept. I don't understand how to use it, but
okay.
Maybe later.
So yeah, I can tell you later, but the general idea is if you want to keep track of your own state root, so you can prove some data follows this and like you can prove that, then you can do this. Also, if you want to optimize, so this is base 16, right? By default, Substrate uses base 16. For some cases, base 2 is better. Base 2 would have smaller nodes, so smaller proof size, but more data hops. So imagine for, I don't know, maybe it's for account balances. You want small proof sizes, so you can send it. So you can have like custom child trie with base 2. So it depends on your use case, and it's not, I think, as much used in Substrate, but it's used few places. And yeah.
Thank you.
Okay, I will just quickly tell you about this, and we will finish it. Choosing base 16 is kind of an opinionated choice. It was, I think, benchmarked to like have a good mix of proof size and IO computation that we chose base 16, but it's not always the best choice for everything. So I'll go through, like, imagine you have base 2, base 16, and our example we saw base 26 and how it looks for proof sizes. So does anybody want to take a guess? So there is this 1, 2, 3, 4. This is base 8 because we could not fit base 16 or base 26. And this is base 2. Can somebody explain like which one will have bigger proof size? So this is base 8. That is base 2. Which one will have bigger proof size?
Base 2 will have.
Base 2 will have bigger proof size. Yeah. Huh? Okay.
Base 2 will have bigger because it needs to hop more, so it will have more.
So when you say proofs, do you want to answer?
e.g. takes less time to increase the value when you're doing when you're basically going to the power of, let's say, the base more or less. So for obviously, for example, to the power 2 for to the power 16 to the power 2 is, well, I don't know off the top of my head, but you get the point.
I don't know if that's actually true, but I'll explain. Okay, you do
mathematical stuff, yeah.
You wanna answer too?
I mean, I think base 8 would be bigger because in base 2, for example, you will need, in this case, to prove a leaf, you will need like 3 extra nodes on the root. But in base 8, you're going to need like the 7 nodes. You're not going to have the 7 nodes, you're going to have 8 hashes when you get the parent. But there are still like 7 hashes instead of like 3.
Yeah, so, yeah, I'll get to it. But, so he was right. So what he said is, in base 8, you will have bigger nodes because it contains hashes of 7 other nodes. Yeah, it's still one hash, but hashes can be big too, and you have 7 hashes. Imagine that. You have to prove this node. You have 4 small nodes. How many hashes you can count? So 1 hash, 2 hash, 3 hash. So ultimately some bytes, right? So if you look at the total value, it contains way less hashes than base 2. So base 2 will have less, smaller proof size.
The proof size, when we say proof size, it's the height of the tree, right? Because this is what we're looking for. And the height for the tree for base 16 will be less than the... but it is because we have more hashes in the...
Exactly. So the height is important when you're doing database hops.
Yes.
So the IO would be more expensive in base 2 because the height will increase.
Yes.
But the proof size itself is actually cheaper in base 2.
Yeah.
So depending on your use case, you can actually, like for child try, and for the normal thing you cannot change, but the child try you can make your base 2 depending on use case, or base 16 or base, I don't know, 100.
It's basically like a trade-off between compression and decompression.
Exactly. Between IO count and proof size in this case. Yeah. And this actually represents a little bit what I said. The node size are smaller in this. It's not, I guess, too apparent, but it's a bit smaller nodes. So, yeah, I didn't find the actual research paper or anything for this, but I have heard around this fact that we chose base 16 even in Ethereum, even in Substrate, because it was like a good middle ground between IO and proof size. But yeah, I mean, if there are some use cases which you want to optimize for one thing, I mean, go for it. So yeah.
Number of path elements, if that increases, that involves the number of hash calculations, and the environment where we don't want to do so many hashes, where I can read more number of memory bytes, but I don't want to necessarily do hashing on them again and again. So there, a smaller number of paths, nodes will be beneficial than having, the size.
Yeah, but then the database reads will become more expensive. So yeah, it's all a trade-off.
Balance has to be there.
Okay, this is the end. We can just recap. We covered there is a key value based storage, but internally it's Merkleized, and how we get the proofs. We learned about large nodes. So if there is a large node, we put the hashes of it and actually put the value to another database key. We learned about unbalanced tree. It can be attack vector. We learned how substrate nodes prunes old data, removes the old data, so it keeps only few block of state. And there are some nodes which are like archive node that keeps state for all the nodes. We learned about like what if base 2, base 16, base 100, whatever you want to take. What are the trade-offs for that? Yeah, that's all. There are a lot of links in the speaker notes if you want to go through them. Yeah, I'm tired. I don't know if you guys are tired, but yeah, thank you. This was your last